Hey, in this tutorial we're looking at section 13.2, which is on the normal distribution. Okay, so our normal distribution has our characteristic bell shape. Okay, something like this. Should be a bit more symmetrical than that one. Okay, because we are symmetric about the mean. So our mean would come in here. Okay, the mean, median and mode are all the same. Okay, if x is normally distributed, is a normal distribution, then we write it as x is a normal distribution, okay, with a mean of whatever and a standard deviation squared. So what you'll see is something like x is normally distributed with a mean of 10, okay, and then a standard deviation of 3 is what that would look like. Okay. Changes to the mean, okay, translate the graph horizontally. Okay, so if we had our mean as 10, okay, and then we change our mean to 15, then the whole graph will move across to the right. Okay, changing the standard deviation will result in a dilation by a factor of 1 on sigma parallel to the y-axis and sigma parallel to the x-axis. So what this means basically is if we change our standard deviation, okay, we're going to stretch or compress the graph as well as make it go up vertically. So we'll stretch it this way, okay, and compress it this way, or we'll shrink it this way and stretch it this way, okay, because the area under our curve always has to equal 1. Okay, so if we're just stretching it one way, and let's say vertically and horizontally, okay, outwards, okay, then we're going to make our area a lot bigger. Okay, so if we stretch it up this way, we've got to shrink it in that way. If we go out that way, we come down this way. Okay, so the normal probability density function is given by, now you're going to hate this, but because it's probably one of the most complicated functions that we've seen, okay, is f of x equals 1 on sigma times the square root of 2 pi times e to the negative a half outside it, x minus the mean on the standard deviation all squared. Okay, now it's actually not as bad as what you think, okay, because once you sub in, okay, your mean and standard deviation, when you sub in your standard deviation, this just becomes a number. Okay, when you sub in your mean and standard deviation, well, we just end up with a number times x up here, essentially. Okay, and it's all squared and that sort of thing, so it's not as bad as what you think. Okay, the max occurs when x equals mu. Okay, so you put in mu here and you'll end up with only 1 over sigma squared. Okay, but that'll end up being our maximum value. Okay, and our maximum occurs at this value here. Okay, because this is all going to end up 0 when x is mu. Okay, because they're going to cancel out. Okay, which means it's going to be e to the 0, which is 1, so we're just left with this for our maximum value. Okay, so our curve also continues infinitely in both directions, so it keeps going on forever in both directions. Alright, so time to start doing a couple of screenshots, okay, because what we talk about here, okay, is our 68, 95 and 99.7 rules. Okay, so we can say that 68% of our information lies within one standard deviation above and below the mean, or another way to think of it is the probability, okay, of a value being within plus or minus 1 standard deviation of the mean is 0.68. Within 2 standard deviations of the mean is 0.95, and within 3 standard deviations of the mean is 0.997. Okay, so I haven't worried about writing on mu minus 3 sigma, etc. on all these pictures here. Okay, but when you look through, you can see, well, if we go from the mean up to 2 standard deviation, well, we're 0.75. 1 standard deviation below to 3 below is 0.1585. Okay, and don't forget these the same either side as well. So if we went from the mean to 2 standard deviations below, we're still going to be 0.475. Okay, so you're thinking of flipping these however you like. I obviously haven't done every combination with them being mirror images, otherwise it's going to be a lot more. Okay, so we get our 0.135 for between 1 and 2, obviously a half for being above. Okay, being between 2 and 3 is 0.0235, between the mean and 1 is 0.35. Okay, just above one end or below one end of 3 standard deviations is 0.0015. below 1 and up to 2 is 0.815. They love using this one in exams. Okay, they really like using that one for some reason. 1 below and 3 standard deviations above is our 0.8385. 1 standard deviation below to anything above is 0.84, so that is past our 3 standard deviations. Okay, and we've got a couple more on this page as well, which is from 2 standard deviations below to 3 above is 0.9735. 2 standard deviations below onwards is 0.975, and 3 standard deviations below upwards is 0.9985. Remember, these are symmetrical, so you could go from our 3 above to anything below would still be 0.9985. Okay, so we need to have a look at some worked examples. So worked example 1. Okay, the probability density function for a normal distribution is given by our function here, which is f of x equals 2 on the square root of 2 pi times e to the power of negative a half times 2 outside of x, take 1, all squared. Okay, we need to state the mean and the standard deviation. Okay, well, usually our standard deviation is down here. Okay, so for our 2 to end up there, we'd have to be dividing by a half. Okay, so our sigma equals a half. Okay, and our mean is equal to 1. We can read that one straight off. Okay, so that's all it looks like. They asked us to sketch it. Okay, sketching it is always a bit tricky. Okay, but we know our mean is up at 1. Okay, and our standard deviations are at a half and 1.5. Okay, 2 and 2.5. And it's going to be 0 and minus a half. Okay, where we're going to be talking, and our highest value, okay, is going to be this part here. Okay, so we're going to go up to 2 on square root of 2 pi. Okay, so we've got to come down something like this. Going to look something like that. Okay, so we'll keep moving on. We'll have a look at worked example 2. Okay, so the heights of women in a particular town are normally distributed with a mean equal to 165 centimetres and a standard deviation, sigma, of 9 centimetres. Okay, what is the approximate probability that a woman chosen at random has a height which is between 156 to 174. Okay, well, you can see here that we're 1 standard deviation below and 1 standard deviation above. Okay, so that falls within our 0.68. Okay, when we have a look back at our pictures here, okay, 1 standard deviation below and above is our 0.68. Okay. Part B is what is the approximate probability that a woman chosen at random will be taller. Okay, so we want to be greater than 174 centimetres. So again, if we have a look back at our pictures, we want to be above 1 standard deviation. Okay, so 1 standard deviation above or below and on, if I can find it here. Maybe that's one I missed. 1 standard deviation above. No, sorry, I might have missed that one. Okay, but that's okay. When we're 1 standard deviation above, sorry, then we're going to be looking at, it's going to be our, sorry, if we look at our below 1 standard deviation, which I believe I did see. Okay, here we go. Our 0.84, okay, is everything else. We want to be on this side. Okay, so it'd have to be 0.16. Okay, for anything below that. So our chances are 0.16. Okay, for part C, what approximate percentage of the women in this particular town are shorter than 147 centimetres. So we want to be less than 147 centimetres. Okay, well that's going to be 2 standard deviation below. Okay, so if we have a look back, okay, we want to be 2 standard deviations above or below. Okay, that's our 3. Where's our 2? Oh, I'm not seeing our 2. Okay, but essentially it's the opposite of this. Okay, because we want it to be below 2 standard deviations. Well, we know what our above 2 standard deviations are. Okay, that's 0.9735, so we can just do 1 minus that. Okay, and we find that we are going to be, our probability is 0.025, okay, which is 2.5%. Okay, so you can see that there was, even after going through all those, I thought of every combination that there was, but already just look at the worked examples, there's a couple more that you could draw in. Okay, and that's fine. Okay, this isn't necessarily an exhaustive list. Okay, but you could absolutely work out what each of them would need to be. Okay, and just fill in a few more. Okay, but generally speaking, these questions aren't going to give you too much trouble. Okay, a lot of them is using this idea. Okay, for some of them, you may need to do some integration work. Okay, but generally speaking, you won't need to do too much at all. If you do need to do some questions where we're using our equation for our normal distribution, our probability density function, okay, if we're using this equation here, okay, and we need to find what the chance is of being a greater than some value that's not one of our standard deviations, okay, you're going to need to integrate, okay, and you're going to do that on the calculator. Okay, that you would absolutely not do anything other than that. Okay, now you could integrate, but you can also use your calculator. You'll have a function in there that's for the normal distribution where you can put in what your mean and standard deviation are, okay, and whether you want to be above or below a certain value, and it'll give you your answer. Okay, so you don't even need to integrate, okay, unless you really, really want to. And look, I wouldn't really be a fan of integrating this and running through everything. Okay, it'll get a bit messy. Okay, you could do it, but I'd probably avoid it, because why make your life harder? Okay, so yeah, hopefully you won't have too many dramas with these questions.